In this lecture, I will explain how using X-ray diffraction order disorder transformation can be determined in a material. Say for example, we have a material CuZn. Now, at a temperature below about 465 degrees C, CuZn compound exists in the what is known as the ordered condition. Above 465, CuZn exists in what is known as disordered condition. There are quite a few cases like that. I will talk about the second compound, say AuCu3. Now, above a temperature of say 395 degrees centigrade, the material exists in a disordered condition, whereas below the temperature of 395 degrees centigrade, AuCu3 exists in what is known as the ordered condition. Now, what is this transformation, ordering or disordering, all about? Now, at sufficiently low temperature, we find an ordered alloy like CuZn or AuCu3 remain in virtually complete ordered condition in the sense that specific lattice sites are occupied by the right kind of atom in almost 100% of cases. Now, let us take the case of CuZn. In CuZn, the unit cell is such, the cubic unit cell, and the 8 corner positions of the unit cell are occupied by copper atoms, and the body centered position is occupied by a gold atom. I am sorry, by a copper atom. So, in CuZn, at low temperature, when we say that it is in the ordered condition, then the 8 corner locations are occupied by copper atoms, and the body centered location is occupied by a gold atom. So, these are the copper atoms at the 8 corners of CuZn. So, these are the copper atoms, whereas the one at the body centered position is a zinc atom. So, this is the situation like in CuZn below a temperature of 465 degrees centigrade. We say that the material is in the ordered condition. What it means? It means that below 465 degrees centigrade, if you look at the lattice of CuZn and you concentrate on a large number of cells, in every unit cell you will find that the corner positions will be occupied by copper atoms and the body centered position will be occupied by zinc atoms. Whichever unit cell you take from the lattice, you will find that this will be the situation. That means, copper atoms will occupy the corner positions of the unit cells, zinc atom will occupy the body centered position in the unit cell. So, we say that the material is in a completely ordered state. Now, when we take CuZn above 465 degrees centigrade, what happens then? So, what happens when we take a piece of CuZn to a temperature above 465 degrees C, then if we look at the different unit cells in the lattice, in some we may find out of 8 corner locations, 7 may be occupied by copper and 1 may be occupied by zinc and another copper would be at the body centered position. In another unit cell, we may have a situation that we have all the 6 or all the 8 corners occupied by zinc atoms and the central atom is made up of copper. In a third one, it may be a different arrangement altogether. That means, whereas in case of the ordered condition, take any unit cell, the same type, one particular type of lattice positions will be occupied by one particular type of atoms and another particular type of lattice position will be occupied by another kind of atom. The situation is totally different when we take this material above 465 degrees C, when we say that the material is in the disordered condition. So, if we look at say just one unit cell above 465 degrees C, it may so happen that out of the 8 corner positions, maybe 7 are occupied by copper and one of the corner atoms is occupied by zinc and there may be a copper in the body centered position. In a second unit cell, it may so happen that 5 of the corner locations are occupied by copper atoms, 3 of the corner locations as well as the body centered location may be occupied by a zinc atom. So, in this way, but all the atoms are arranged in the extended crystal in such a manner that the average composition shows CuZn, it does not depart from that. So, the composition of the material does not change, but above 465 degrees centigrade, the arrangement of the atoms at different locations of the unit cell is completely haphazard. We say that the material is in what is known as the disordered condition. The material is in the disordered condition. Now, when ordering takes place from disordered CuZn or when disordering takes place from ordered CuZn, what happens to the properties of the material? There are subtle changes in properties which we observe during a order disorder transformation. For example, CuZn, when it is in an ordered condition, it has a high value of electrical conductivity. In the disordered condition, the electrical conductivity is much lower. Then the hardness of ordered CuZn is higher than the hardness of disordered CuZn. So, you see that due to an order disorder transformation in a material, properties do change. But when you look at the microstructure of CuZn at a temperature below 465 and also at a temperature above 465, microstructure wise there is no change, and of course, composition wise also there is no change, but this kind of transformation leads to some changes in the material properties. So, how to figure out whether such a transformation has already taken place or not? That means, it is very necessary to know whether there has been a order disorder transformation in the material, because since the composition does not change, a microstructure does not change. So, usual ways of finding out the transformation are of no use, but X-ray diffraction provides a unique method by which we can determine the order disorder transformation in materials. Now, if we look at CuZn in an ordered condition and in a disordered condition, you see disordering may be to a very high extent, disordering may be of a very low extent. So, how to depending on how in the disordered material the atoms are arranged in the different unit cells. So, how to determine the degree of order or disorder? Now, as the temperature is raised and the critical temperature Tc is approached, so this temperature is a critical temperature for CuZn, this temperature is a critical temperature for AuCu3. Gradually some randomness in atomic arrangement sets in, and as we go above the critical temperature more and more, this randomness goes on increasing. So, the departure from perfect order can be expressed by what is known as the long range order parameter, which is S equal to x a minus y a divided by 1 minus y a. So, what is x a? X a is a fraction of a sites which are actually occupied by the right kind of atoms. Here A atoms, and Y A is a fraction of A atoms present in the alloy. Say for example, if we look at the CuZn case, what it says that S of the degree of order is equal to x a minus y a divided by 1 minus y a. So, what is x a? It is a fraction of A sites which are actually occupied by the right kind of atoms. Now, what are the two different sites available to the copper and zinc atoms in a unit cell of CuZn? One corner site one corner site in the ordered condition by copper atoms and one body centered cubic site to be occupied by zinc atoms. So, it says that long range order parameter can be determined from this expression where x A is the fraction of A sites which are actually occupied by the right kind of atoms, here A atoms. So, what is the fraction of corner sites occupied by copper in a perfectly ordered alloy? 1. In a perfectly ordered alloy, the X A, the type of a particular site, the fraction of the right kind of atoms to occupy that particular site is 1 fraction, because in ordered case all the corner atoms are occupied by copper. So, the value of X A simply becomes 1. So, in case of ordered AuCu3, in case of ordered ordered CuZn, the degree of order is equal to X A minus Y A by 1 minus Y A, where X A is a fraction of a particular site which is actually occupied by the right kind of atom. So, here the fraction of corner sites are occupied by copper. So, entire this fraction, all the corner sites are occupied by copper in ordered condition. So, this fraction is equal to 1. And what about Y A? Y A is a fraction of A atoms present in the alloy. Anyway, so because this is 1, so S for an ordered CuZn or an ordered AuCu3 will be 1 minus Y A divided by 1 minus Y A equal to 1. So, we see that the degree of long range order S, that for a completely ordered material will have the S parameter equal to 1. Now, when we are talking about the compound CuZn, what will happen to the X-ray diffraction pattern of CuZn when it is in a completely ordered condition and in a completely disordered condition? We are going to find out. Say for example, when CuZn is perfectly ordered. So, when CuZn is perfectly ordered, then we know that one corner site with fractional coordinates 0, 0, 0 will be occupied by copper. So, copper, there will be one copper atom at the fractional site 0, 0, 0, and there will be a zinc atom at the fractional site half, half, half. So, when CuZn is in a perfectly ordered condition, then what will happen to the crystal structure factor of the material? So, crystal structure factor of the material will be the equal to F times, and you see here there are two kinds of atoms. So, the atomic scattering factors of these two atoms will be different. So, when we look at the crystal structure factor and find it out for all the atoms belonging to the unit cell, then so far as the copper atom is concerned, it is FCu exponential 2 pi I into H equal to 0 plus K equal to 0 plus L equal to 0 plus, now we talk about the zinc atom. So, it is FZn for the zinc exponential 2 pi I H into half plus K into half plus L into half. So, it will be FCU exponential, this will be 0. So, this value will be simply 1, exponential 2 pi I to 0 will be 1. So, it will be FCU plus FZn exponential pi I into H plus K plus L. Now, this is the crystal structure factor for a unit cell of ordered CuZn. Now, there can be two situations arising. In one case, H plus K plus L can be an even quantity. So, if H plus K plus L is an even quantity, then what will happen to this expression exponential pi I into H plus K plus L? It will be plus 1. Okay? So, it will be FCU plus 1 into FZn. So, it is FZn. What is the other possibility? H plus K plus L is equal to an odd quantity. H plus K plus L is equal to an odd quantity. So, what will happen when H plus K plus L is an odd quantity? This expression will be simply equal to minus 1. As a result, the value of F will be equal to FCU minus FZn. So, you see that when CuZn is in a perfectly ordered condition in the sense that all corner atoms are occupied by copper atoms and all body centered positions are occupied by zinc atom, then we figure out that F, the crystal structure factor for the unit cell of ordered CuZn, will be equal to FCU, atomic scattering factor of copper, plus FZn, the atomic scattering factor of zinc, when H plus K plus L is an even quantity, and it will be FCU minus FZn when H plus K plus L is an odd quantity. Now, you see that in the intensity equation, F will always appear in the form of F square. F will always appear in the form of F square. So, whether H plus K plus L is even or odd, the square of these terms will always be positive, which means diffracted intensity will be produced from planes for which H plus K plus L are even, and also from the planes for which H plus K plus L is equal to odd. So, this is a very important observation. So, simply by calculating the value of crystal structure factor for ordered CuZn, we find that the value of the crystal structure factor will be FCU plus FZn when H plus K plus L is an even quantity, and it will be FCU minus FZn when H plus K plus L is an odd quantity. So, from all kinds of planes there will be diffraction, because in the diffracted intensity F appears as F square, as we know. So, the square of this quantity and the square of this quantity are all positive, Now, the value of this quantity f square in this case is much higher than over there. Okay, the value of this value is much larger than this value. That means, some of the lines, their intensity will be much higher, and which are those planes? Those are the h plus k plus l is equal to even planes, but those planes for which h plus k plus l is odd, for them the intensity will be proportional to this square, which will be less than in the previous case. Now, we will examine the situation where CuZn is in the disordered condition. So, now we will examine the situation where CuZn is in the disordered condition. Here, depending on the large number of unit cells, the arrangement of the copper and zinc atoms, so far as the respective sites are concerned, can be very, very different. So, under such circumstances, how do we study this material? So, what we want to do now, just as for copper zinc ordered condition, we try to figure out the value of crystal structure factor, and from there we try to determine from which HKL planes the diffracted intensity will be much higher than from other planes. In a similar manner, we will try to find out the value of crystal structure factor F for CuZn in the disordered condition. Now, let us see how we can do that. You see, when the material is in a completely disordered condition, the situation changes from one unit cell to another. So, how do we know the exactly which atoms are occupying which types of sites in this particular case? In order to avoid the difficulty, we assume that when CuZn is in a disordered condition, we can consider each lattice point to be occupied by what is known as an average copper zinc atom, You see, from unit cell to unit cell, the situation will be different. In some unit cells, 7 corner atoms may be occupied by copper atoms, then one of the corner atoms may be occupied by zinc, body centered atom may be occupied by copper, in some other it is again a different kind of arrangement, in some other again a different kind of arrangement. The only thing that we know that the composition of the material as a whole does not change. So, we can consider as if in CuZn disordered condition, we have what is known as an average CuZn atoms, and what kind of characteristic this average CuZn atom will be? From chemical composition we find per unit cell there is one copper and one zinc atom. So, we can say that an average copper zinc atom will have half the characteristic of copper and half the characteristic of zinc. So, an average copper zinc atom we can take as one which will have half the characteristic of copper and half the characteristic of zinc. So, what will be the atomic scattering factors for this? It will be half F Cu plus half Fzn. So, you see that this will be the atomic scattering factor for an atom which is the average copper zinc atom. So, F average for this average CuZn atom will be equal to half FCu plus half Zn. Now, we can calculate the crystal structure factor F for disordered CuZn. Now, if we do that, we can write capital F is equal to, now there are two atoms, one is at 0 0 0 location, the other one at half of half location, and we have got average CuZn atom at both the locations. So, we can write capital F is equal to F average into exponential 2 pi I h into 0 plus k into 0 plus L into 0 plus F average exponential 2 pi I into h into half plus k into half and L into half. So, this is equal to F average into 1 plus exponential pi I h plus k plus L. So, you see that the crystal structure factor in the disordered condition for CuZn, it can be written as F average into 1 plus exponential pi I into h plus k plus L. But again, if we look at the situation where h plus k plus L is equal to an even quantity, where h plus k plus L is an even quantity, then what will happen to this expression? If h plus k plus L is even quantity, then this term here will have the value of plus 1. So, capital F will be equal to F average into 1 plus 1 2. So, it will be 2 times F average, but we know that what is F average? F average is half FCu plus half FZn. So, we can write 2 into half FCu plus half FZn. So, that will give us the value of FCu plus FZn. What about when H plus K plus L is equal to an odd quantity? Now, in this expression, this will become minus 1. If H plus K plus L is an odd quantity, this will have a value of minus 1. So, capital F will have a value of F average into 1 minus 1. That means, capital F becomes equal to 0. So, we see a very clear cut case that when you have planes, atomic planes for which H plus K plus L is an even quantity, then for the ordered CuZn, F becomes equal to FCu plus FZn. So, that F square becomes FCu plus FZn square. When we come to the disordered CuZn, again we find that F becomes equal to FCu plus FZn, and therefore, In this case also, capital F square will be equal to FCU plus FZN square. So, this is the same value as we get over here. So, it says whether CuZn exists in the ordered form or in the disordered form, we will say that the crystal structure factor for atomic planes for which H plus K plus L is equal to an even quantity will be the same. For example, FCU plus FZN. What happens when we look into those planes for which H plus K plus L is an odd quantity? Now, when the material is in the ordered condition for H plus K plus L is equal to odd, we find that F square is FCU minus FZN square. What happens in the disordered condition? Well, F is equal to 0 and therefore, F square is equal to 0. So, you see that F square appears in the equation for integrated intensity. So, naturally, if F square is 0, there will be no intensity. So, what does this calculation shows? We find that if you have CuZn in an ordered condition and in the disordered condition, there will be a strong diffracted intensity from those planes for which H plus K plus L is an even quantity, both in respect of ordered as well as disordered CuZn. On the other hand, if we consider the planes for which H plus K plus L is an odd quantity, we will find that the diffracted intensity from those planes will also be there in case of the ordered material, but the diffracted intensity will simply be 0 in case of the disordered material. That means, the ordered material will show diffraction lines from planes for which H plus K plus L is even, as well as from planes for which H plus K plus L is odd. On the other hand, when CuZn is in the disordered condition, then the diffraction will occur when H plus from those planes for which H plus K plus L is even, and there will be no diffraction taking place from H plus K plus L is equal to odd planes. So, you see that if we have two diffraction patterns, one for ordered CuZn and the other for disordered CuZn, then the ordered material, the diffraction pattern of the ordered material will show lot more lines. Why? Because both type of planes for which H plus K plus L is even and H plus K plus L is equal to odd will give rise to diffraction. On the other hand, the disordered structure, if we take a diffraction pattern, will show fewer lines, because here only diffraction will occur for those planes for which H plus K plus L is an even quantity. No diffraction will take place from planes for which H plus K plus L is an odd quantity. So, the diffraction pattern of an ordered material shows lot more lines as compared to the diffraction pattern from a disordered material. Now, you see the value of F square here may be very low than over here. So, you see that for those planes for which H plus K plus L is equal to even, the intensity values of the lines appearing in the diffraction pattern of both the materials will be of similar degree. But when it comes to the H plus K plus L odd planes, in the ordered material, they will give a weak intensity for such planes, and over here the intensity will not be there, that means those lines will be absent. In a similar way, we can do the calculations for what is the difference between the diffraction pattern from ordered AuCu3 and disordered AuCu3. So, you say that the lines which are common in the ordered and disordered CuZn, the common lines are known as the fundamental lines. The fundamental lines are common in the XRD of both ordered and disordered CuZn. The extra lines which appear in the diffraction pattern of the ordered material, those are known as the superlattice lines. Those are known as the superlattice lines. Obviously, the intensity of the superlattice lines will be much less as compared to the fundamental lines because of this reason. Here FCu, it is FCu plus FZn square in case of H plus K plus L is even, and in this case when H plus K plus L is odd, F square is FCu minus FZn square. Naturally, the superlattice lines are much weaker compared to the fundamental lines. Now, we can do a similar exercise for the ordered AuCu3 and disordered AuCu3. You see, in an ordered AuCu3 material, the corner sides will be occupied by the gold atoms and the face centered positions are occupied by the copper atoms. So, the chemical, you see, one corner atom plus 3 of gold and 3 face centered atoms of copper. So, there are 4 atoms per unit cell in this particular case. Now, in the disordered case, what will happen? Again, we will have a difficult situation because the arrangement will vary from unit cell to unit cell. So, we consider an average gold copper atom, and because the chemical composition is AuCu3, so there is one gold atom out of 4 atoms present in the unit cell and 3 copper atoms out of 4 in the unit cell. We say that now we will have an average atom at all the lattice locations, and this will have 1/4 the characteristic of gold and 3/4 the characteristic of copper. You can see that the copper atoms are blue colors and gold atoms are yellow colors. So, each average atom we will consider to be made up of such that 1/4 is the characteristic of gold, 1 and 3/4 is the characteristic of copper. And again, as we did with respect to CuZn, we know that in case of ordered AuCu3, we can find out that the corner locations are 0, 0, 0. So, for ordered AuCu3, we know that the corner sides are occupied by the gold atoms, and so there will be one gold atom per unit cell and there will be 3 copper atoms per unit cell. And what are the fractional coordinates? This one gold atom, its fractional coordinates are 0, 0, 0. And what about these 3 copper atoms per unit cell? Half, half, 0, half, 0, half, and 0, half, half. So, in case of the ordered AuCu3, since an average AuCu atom has got 1/4 the characteristic of gold and 3/4 the characteristic of copper, then the average gold copper atom will have an atomic scattering factor given by 1/4 FAU plus 3/4 FCU. So, this will be the atomic scattering factor for the average gold copper atom. So, if we now write down an expression for capital F crystal structure factor, so it will be 1/4 FAU plus 3/4 FCU, then this is the thing. So, let us talk about the disordered AuCu3 first. So, what I am doing is for the disordered AuCu3 first. So, for the disordered AuCu3, we will have an average gold copper atom at all the locations 0 0 0, half half 0, half 0 half and 0 half half. So, we will have a situation where the F can be written for disordered AuCu3 in this manner. It will be 1/4 FCU FAU plus 3/4 FCU multiplied by exponential 2 pi I into h into 0 plus k into 0 plus L into 0. So, it will be simply equal to 1 plus we can write down for the other 3 locations exponential pi I into h plus k plus exponential pi I k plus L plus exponential pi I h plus L. So, you see that this is the expression for the capital F for the disordered AuCu3. Now, if HKL are unmixed, if HKL are unmixed, that means all are odd or all are even, then what will happen? If HKL are unmixed, that means all are odd or all are even. In that case, H plus K, K plus L, H plus L, these are all even quantities. So, their values are 1, plus 1, plus 1 and plus 1. So, when HKL are mixed quantities, capital F will be equal to 1/4 FAU plus 3/4 FCU multiplied by 4. So, it will be equal to FAU plus F3 FCU. So, this will be the value of crystal structure factor in case of the disordered AuCu3 when HKL are unmixed. But when HKL are mixed, what will happen? When HKL are mixed, that means some are odd, some are even, then what will happen? Out of these 3 quantities, one will be plus 1, the other 2 will be minus 1. As a result, the value of capital F will be simply equal to this quantity multiplied by 0, that means 0. So, you see that when we have AuCu3 in a totally disordered condition, then when we have a completely disordered condition, here for example, it is written ordered AuCu3, it is not true, it is a disordered AuCu3, and that is why we have taken an average gold copper atom at all the lattice sites. So, if we do that, what we find in the disordered condition when HKL are unmixed quantities, the value of capital F is FAU plus 3 FCU. On the other hand, for all cases where HKL are mixed quantities, we find F becomes equal to 0. So, it shows that when AuCu3 exists in the disordered form, then we will have diffraction lines only from those planes for which HKL are unmixed quantity, and no diffraction line from all those planes where HKL are mixed quantities. Now, if we find out the values of F for ordered AuCu3, then what will happen? In case of ordered AuCu3, we know that the corner atoms are occupied by the gold atoms, corner locations are occupied by the gold atoms, and face centered positions are occupied by copper atom. So, if now we talk about ordered AuCu3, we know that the 0, 0, 0 locations, the corner locations will be occupied by the gold atoms, whereas half half 0, 0 half half and half 0 half locations will be occupied by copper atoms. So, in this case, if we want to figure out what the value of capital F is going to be, then we have to do the summation over one gold atom. So, FAU into exponential 2 pi I into h into 0 plus k into 0 plus L into 0. So, the whole thing will be 0 here, plus FCU, we will have exponential 2 pi I h into half plus k into half plus L into 0, etc., etc. So, it can be written as exponential pi I into h plus k plus exponential pi I into k plus L plus exponential pi I into h plus L. Now, again we find that, and this value is simply equal to 1, because exponential 2 pi I 0 is simply equal to 1. So, we can write down, instead of this, we can write down simply FAU. So, now let us consider two different cases. In one case, say HKL are unmixed quantities. When HKL are unmixed quantities, then what will happen? Either all odd or all even. Then this will be an even quantity, this will be an even quantity, this will be an even quantity. So, the value of this will be 1 plus 1, this will be the value of what will be plus 1 plus 1. So, you see that when HKL are unmixed, capital F becomes simply equal to FAU plus 3 FCU. So, this is the value of the crystal structure factor when HKL unmixed in case of an ordered AuCu3. What happens when HKL are mixed quantities? What happens when HKL are mixed quantities? When they are mixed quantities, one of these will be plus 1, one of these will be even, other two will be odd. As a result, it will be 1 minus 1 minus 1. So, we will find that it will be simply capital F is equal to FAU minus FCU. So, you see that when we consider the disordered AuCu3, we find that diffraction will be possible from only those planes for which HKL are unmixed. No diffraction will happen from those planes for which HKL are mixed, because F is 0. On the other hand, when the material is in the disordered condition, then diffraction will take place not only from the planes for which HKL are unmixed, but also from the planes for which HKL are mixed. And as usual, the lines which will be obtained from planes having HKL unmixed quantities in both the patterns are known as the fundamental lines. When we consider the HKL unmixed planes, we will have diffraction taking place from those planes both in the ordered condition and in the disordered condition. However, when we talk about the HKL mixed planes, there will be diffraction from those planes in case of the ordered alloy, but not in case of the disordered alloy. So, as a result, we will see the number of lines, diffraction lines which will appear in the diffraction pattern of ordered AuCu3 will be more than the number of lines which appear in the diffraction pattern of disordered AuCu3. And this is the way we can distinguish an ordered material and the disordered material. The ordered materials will show more number of lines, the fundamental lines as well as the superlattice lines, but in the disordered material only the fundamental lines will be obtained, not the superlattice lines. So, absence of superlattice lines in the diffraction pattern of disordered CuZn or AuCu3 will show that those are in a disordered state. So, absence of the superlattice lines from the diffraction pattern of AuCu3 or CuZn will indicate that those are in a disordered condition.